Okay, so today we will start with the topic of stream ciphers. So, as we were discussing in the last day's class, we were discussing about block ciphers, and also we finished with the modes of block ciphers. Okay. So, what we saw, I mean, typically is that we saw certain, we know what is the definition of block ciphers, and we know how to use block ciphers. Okay. So, therefore, there were certain modes that we defined. Out of them, if you remember that the last few modes which were defined were essentially slightly different from the definition of block ciphers. Okay. So, they were applied more something like a stream cipher. Okay. So, anyway, so we will take up the topic of stream cipher more formally and try to understand the principles behind the constructions. Okay. So, first we will discuss with the classifications that exists in the stream cipher world. Okay. And then we will start with a very interesting topic and important also, that is about feedback based stream ciphers. Okay. So, we will talk about LFSRs, linear feedback shift registers, and also define something which is called M sequences, which are very much used to generate something which is called pseudo randomness in cryptography. Okay. So, we will try to understand the basic principles, but since we know what is, or rather we have studied block ciphers, let us start with the difference between block and stream ciphers. Okay. So, the differences are not very much definitive. So, it means that exactly clearly differentiating between the two is slightly tricky, but we can say in this way that block ciphers essentially process the plain text which operates on large blocks of data. Okay. But as opposed to that, stream ciphers will operate on small blocks of data. Okay. So, this is a very sort of we can say a not very perfect or not very accurate difference, but this can be used to essentially differentiate between block ciphers and stream ciphers. Okay. Another important difference which we can say is that the block ciphers. Okay. So, if you remember the block ciphers are essentially, the pure block ciphers are essentially memoryless. So, what does it mean? It means that the output at particular time, say time t, does not depend upon what happened at time t minus 1. Okay. So, therefore, all the operations of your encryption functions are independent of your previous operation. Okay. So, this was, so when I say it is a pure block cipher mode, we remember about the ECB mode. Okay. So, in such kind of scenario, block ciphers were memoryless. Okay. But by definition, we will see that our stream ciphers are essentially having a component of memory. Okay. So, that means that it does not, in case of stream ciphers, the ciphers that you produce are not a resultant of only the plain text or the key, but also something which we call as a state. Okay. So, that is something which is called a state or a state variable which gets updated as the time goes by. Okay. And your output depends not only upon your plain text and your key, but it also depends upon the current state. Okay. So, these are the broad differences, but as we remember that in case of block ciphers, like the modes that we had, like the mode like OFP mode and CFP mode and so on, they were essentially more like stream ciphers. Okay. So, keeping this difference in mind and also the caveat, what we will do is we will go ahead with this definition of stream ciphers. Okay. So, let us start with something which we have already seen, which we call as a one time pad. Okay. So, one time pad is a first starting example of stream ciphers. Okay. So, therefore, if you remember, the idea was very simple, that for I varying from 1 to 3 and so on, your ciphertext Ci is obtained by the XORing of your message and your corresponding key value. Okay. So, this we call also the one time cipher, and this was defined over the binary alphabet, right. So, we say that it was unconditionally secured, and we also proved this result. Okay, that we saw this, that Hk is greater than equal to Hm. So, what does it mean? That is, the entropy of your key should be at least equal to that of your message entropy. Okay. So, that means that you have got a large key value. So, what is the problem that we saw with this? The problem was that we had a large key to handle. Okay. So, we want, so in case of practical scenario, what we will typically want is that we will try to ensure that Hk value is actually less than Hm. The moment we see that, we know that we are not getting something which is called as unconditional security, right. So, what we strive for is computational security, that is we are striving for the fact that suppose an adversary has got a bounded power, that is computationally bounded, we are trying to guarantee security against such kind of adversary. Okay. So, that is the model. So, therefore, that is the intent. So, therefore, the intent is protection against a computationally bounded adversary. Okay. So, what we will see in all the studies that we do about stream ciphers is that we will try to again produce this key stream Ki. So, if you see the one time pad, we will try to produce this Ki, but with a smaller key. Okay. So, in case of one time pad, we had the size of the key at least equal to that of the message size, right. But in case of practical stream ciphers, we will try to produce this key stream and make it look as much random as we can, okay, but we will start with a smaller key. Okay, that is the initial key should be much lesser than that of the message size, right. Only then it becomes practical, correct. So, the first class of stream ciphers that we will see is something which is called a synchronous stream cipher. So, what is a synchronous stream cipher? A synchronous stream cipher is such kind of stream ciphers for which your key stream is generated independent of your plain text or cipher text. Okay. So, that means it does not depend upon when the plain text comes or when the cipher text comes, okay, but it proceeds quite independently. Okay. So, the encryption process which we can essentially differentiate or divide this into three basic parts. The first part will update a state variable. Okay. So, therefore, as I told you that these kind of stream ciphers has got a state variable. So, there is a state variable which we denote by say sigma, and this value of the state variable gets updated during the encryption procedure. Okay. So, there is a function say f which takes in sigma I and also the secret key value. So, you see that we start with a smaller key, okay, and using this smaller key we actually carry on iterations to generate a large key stream. Okay. So, we start with a smaller key and we keep on iterating certain processes or procedures to get a larger key, okay, or to get a larger key stream. So, what we do is that we take this sigma I and we take this key starting key and we operate this function f and we obtain sigma I plus 1. Okay. So, remember that this function f, g and h are all known in the public domain. Okay. So, what is secret? Only this key value is secret, that is this k value is secret. Okay. So, we start with an initial vector. So, immediately you can understand that in order to start you require a sigma 0, right. So, this sigma 0 is commonly known as the IV or the initialization vector. Okay. So, we start with an IV and we keep on repeating this process and we obtain something and we keep on updating the state variables. Okay. So, then what we see is that whenever, so therefore, then what we do is that based upon this sigma I and this k value we generate zi which is used to denote the key stream. Okay. Now, the moment we see that the cipher text the message comes like mi comes in, we operate mi and zi and obtain the corresponding cipher text ci. So, here you see that this zi or this key stream zi can be generated ahead of time, right. It does not depend when the corresponding plain text comes in, right, and that is why it is called a synchronous stream cipher. It does not depend or it can be generated independent of the plain text or of the cipher text. Okay. Plain text during encryption and cipher text during decryption, right. So, therefore, an example of this could be a binary additive stream cipher. So, in that case what we do is that this corresponding h function is nothing but the XOR, that is you take zi and you XOR that with mi. So, you see that when we do that the definition or rather the description is quite similar to the one time pad, right. So, only in this case what is the difference? In this case this corresponding key stream is generated actually from a smaller key using a deterministic algorithm, right. So, therefore, that is the basic difference between these class of stream ciphers which are practical from a one time pad, okay. And that is why this is not unconditionally secured, but what we are only guaranteeing is that we are trying to make it secured against a computationally bounded adversary. So, that is the definition of synchronous stream ciphers. So, this is a pictographic description. So, you can see that It is the same thing, like we take sigma I, which is the state variable, and there is a corresponding k value using both these things. What we are doing essentially is that we are keeping on using the function f, we are keeping on updating this state variable function. The moment we have this corresponding state variable, we take the state variable, operate upon the key also, and we obtain the key stream, which we act upon the corresponding message to get the ciphertext, right. So, decryption is quite simple. You can see easily that what you do is that you again take the k, and you can do this same operation here also, because it does not depend upon your plain text, right. You take this sigma I, you take g, you can obtain this key stream ahead of time again, and in this case you require the inverse operation of h, right. So, if this was a modulo XOR, then this would have been the same operation, right, because modulo inverse is, modulo XOR is self invertible, right. So, therefore, you can see that you can make quite simple cipher structures using that, right, using this kind of things, and they are quite fast, right, and that is the reason why stream ciphers are quite popular. So, they were very much popular and still are quite popular. Okay. So, the properties of, so let us study some properties of these ciphers. So, we will essentially try to first of all understand one important difference that we will see with another type of ciphers that we will see next, is something which is called the requirement for synchronization. That is, you can see one thing, that is, when you are encrypting and you are sending the data to the corresponding decryptor, then this what can happen in between is that this ciphertext can get damaged, right, because of maybe due to accidental reasons or due to malicious reasons. Okay. So, for example, even due to communication errors, there can be errors introduced in this ciphertext. Okay. So, the moment you see that, for example, so there can be two kind of damages. One in which you can drop some CI values, okay, that is, you can delete some CI values and also insert, and the other when you modify some CI values. Okay. So, in both the cases, in the decryption end, at the decryption end, there will be two types of events that occur. Okay. So, can you see that? Like, for example, let us consider first that I take CI, I have got the stream of CIs coming in, right, and I just change, say, for example, a 1 to 0. So, imagine a binary alphabet. Okay. I just change a 1 to 0. What will happen? Only that particular MI would get changed, right, rest of the things will work fine, right. So, you see that if there is a corresponding change in the corresponding ciphertext, then the decryptor will not be able to figure out, except the fact that only one particular bit has got changed, rest of the things will take place fine. Okay. So, this can be a problem in certain kind of applications of these ciphers, like for example, if I want to also ensure that my integrity of data is maintained. Okay. So, there can be a problem in such kind of scenarios. Okay. So, consider another case where I drop some packets, like I take CI for example, and I start dropping some values of CIs. Then what will happen? Then there will be a disaster actually at the decryption end. You see that if I start doing that, then there will be a total loss of synchronization. Okay. So, you see that if I start dropping or deleting some values of CI or inserting some extra values of CI into the stream, then there will be a complete desynchronization between the encryption and the decryption portions. Okay. So, how do you recover? The only way to recover would be to reset, right, to start again from the scratch, or what we can do is like what we do in typical examples of networks, we can actually have some demarkers, right, we can have some markers. Okay. But you see that this is adding to the complexity of your job. Okay. So, we would actually would have wanted another kind, a class of stream ciphers where we can alleviate this problem, right. So, therefore, that is the thing which we have mentioned here. So, let us again read out these properties. So, it says that the sender and the receiver must be synchronized, that is using the same key and operating at the same state with that key, okay, within that key. So, insertion or deletion may cause loss of synchronization. Okay. Resynchronization may need reinitialization and or special marks in the stream at regular intervals. Okay. Similarly, you see that there are no error propagation. So, if I just modify one digit, only that corresponding digit gets modified. Okay. So, this essentially leads to certain kinds of active attacks, can lead to active attacks. Like for example, if I insert, delete or replay, okay, then this cause loss of synchronization. Okay. And immediately you see that this is detected by the decryptor, because in such kind of things there is a complete havoc taking place at the decryption end, right. So, I can possibly figure out that these kind of things have taken place, like there has been some ciphertext being inserted or deleted. Okay. So, therefore, you see that I can ensure this kind of that I am able to, at the decryption end, I am able to figure out that such kind of malice has taken place. Okay. But if you just, for example, change a particular ciphertext value, then I am not so easy, then it is not so easy to figure it out. Okay. Because in that case the rest of the decryption takes place fine and only few changes occur. Okay. So, if you see that at the decryption end, if large number of changes occur, then it will be easy for me to understand, right. So, therefore, if you actually delete or insert some ciphertext values, that becomes easy. Okay. But if you change some values, then you are not able to figure out, right. So, therefore, in this class of stream ciphers, what we see is that if we change some ciphertext values, okay, then it becomes easier to capture at the decryption end. But if you insert or delete, I mean sorry, the other way around, if you insert or delete, it becomes easy to capture, but if you actually just change or modify some ciphertext values, say one ciphertext value, then it is not so easy to capture. Okay. So, this is actually quite different from another class of stream ciphers, which we call as self synchronization stream ciphers. Okay. So, what is a self synchronization stream cipher? We will just see. So, it is an asynchronous stream cipher as opposed to the previous one. It is one in which the key stream is generated as a function of the key and a fixed number of previous ciphertext digits. Okay. So, therefore, in this case I think what you can see like this, that is, if you for example consider a window of ciphertexts. Okay. So, let us consider a window of size t. Okay. And therefore, what we see is that if the corresponding state variable sigma I depends only upon this window of size t. Okay. And therefore, this is an essential difference between the previous class of stream ciphers and this. Why? Now, because if the error occurs anywhere outside this window, then there is no problem in the decryption end. Okay. The problem occurs only if there is an error inside this window. Okay. So, that means this helps, this property helps to automatically recover. Okay. So, I think it will be clear with this diagram and with this description, that is, for example, you consider this window of size t like Ci minus 1 to Ci minus t. So, you considered Ci minus t, Ci minus t plus 1 and so on till Ci minus 1. So, this determines your sigma I value, and then just like in the previous case, you operate take sigma I, take key k and operate g and obtain the stream zi, and then again operate upon zi and mi to obtain your corresponding ciphertext value. Okay. So, in this case the initial state will look like this. Okay. So, if you just consider the diagram, you see that it will look like this. So, you have got a window of ciphertexts. Okay. This operates upon your g value and gives you, I mean your g value takes these ciphertext values, takes the key k and obtains the stream cipher zi. Okay. Now, this zi and your message mi gets operated with the function h. It could be a simple XOR and you operate the value of Ci. Okay. What do you do at the decryption end is exactly the opposite, right. So, you take again these ciphertexts and again take this function h, okay, and take this function g, obtain the key stream, act upon the inverse of h and obtain back the plain text. Okay. So, what is the difference? You see in this case synchronization becomes easy. Why? It is simple, right, because you see that in this particular diagram, if there are errors only in this window, then you have a problem. Okay. Otherwise, it is fine. So, suppose there has been some deletions that take place, some modifications that take place, Okay. As long as the effect of this persists, you will find that the corresponding decryptions will be faulty, but after the problem vanishes, then actually your decryption works fine. Okay. So, therefore, if there is even if there is a problem, you can eventually get out of that problem, right. So, therefore, you see that and actually we have seen such kind of scenario in a particular mode of block cipher. Can you tell me what? In a cipher feedback block. Okay. If you remember, we had an R bit left shift there. Okay. So, I will come to that, but I mean we have already seen that example. Okay. So, in this case you see that self synchronization is possible. Okay. So, if there are insertions and deletions, then at most t digits may be lost. Okay. So, if there are at most t digits which are lost, I can still get out of this problem. Okay. So, limited error propagation, that is one digit modification or insertion or deletion may cause incorrect decryption of up to t digits. This is also another difference from the previous one. In case of previous that is synchronous stream ciphers, what we have seen is that if you modify only a particular ciphertext Ci, then only that particular digit in your plaintext gets modified. Okay. But here a particular ciphertext has got a control over t decryptions. Okay. So, therefore, t even if there is a modification in only one single bit, okay, or in one single digit, then you will find that there will be corresponding problems in the decryption for t number of times. Okay. So, in this case you see that just the opposite, like if there is an insertion or a deletion, okay, then it is hard to catch, because you are finally getting out of that problem. Okay. After t such kind of decryptions, you will finally eventually end up with. So, I mean when I say easier or hard, I am comparing with the synchronous stream ciphers. Okay. So, in case of synchronous stream ciphers, if there was an insertion or a deletion, then there was a total problem. Subsequently, all the decryptions would have been faulty. Okay. In this case, after t such kind of decryptions, finally the problem is solved. It is finally again synchronized. Okay. So, that way it is, I mean, harder to catch if there is an insertion or deletion. In case of self synchronizing stream ciphers, it is harder to catch compared with a synchronous stream cipher. Okay. But whereas if there is a say a modification, that is a 1 bit error or something like that, then in case of these class of stream ciphers, okay, what happens is that you find that t decryptions are faulty, but in case of your synchronous stream ciphers, only one digit was faulty. Okay. So, therefore, these are the basic differences between this class of stream ciphers and the previous stream ciphers. Okay. So, what we just as a note, you can note that the diffusion of the plain text statistics is better in case of this kind of self synchronizing stream ciphers, but even then there are attacks. Okay. Like you can see that in the previous case it was easier, you can just reflect upon this fact, it was easier to mount a known plain text attack. Okay. But in this case it is easier to mount a known ciphertext attack, chosen ciphertext attack. Okay. And there are attacks actually even on quite contemporary stream ciphers of this class. Okay. So, now this is just a recap of what we have what we have already seen. So, in case of CFP, I have just replaced this R by 1. Okay. So, this is 1 bit CFP. So, you remember that this was the diagram, right. So, you see that after, so how we already said that if there is an error, then the error at the decryption will remain as long as this corresponding error remains in this register I, right. After that, after the effect after the effect disappears, you again get correct decryption. Okay. So, you see that this is an example of self synchronizing stream cipher. Okay. So, then we come to something which is quite interesting, it is called feedback shift register and quite involved also. So, they are essentially basic blocks of many key stream ciphers, key streams generators, and we will essentially study a very important class of feedback shift registers. It is called LFSR or linear feedback shift register. Okay. So, it is very well suited for hardware implementations, and it can also produce sequences of very large period. Okay. So, therefore, this property is very much required for stream ciphers. That is, what we want is that we want a large period in the stream ciphers. Okay. So, we do not want small cycles, we want that the repetitions will take place after a large number of times. Okay. And it should also have good statistical properties. Now, what are good statistical properties? I have actually not defined, okay, but we will take up this issue in our subsequent class on pseudo randomness. Okay. So, at this point of time, just imagine that good statistical properties mean that it should look as much random as possible. Okay. So, and this can be actually analyzed by algebraic techniques also. So, therefore, this analysis or this amenability to analysis helps us to understand the security of these kind of ciphers. Okay. So, we will see that there will be problems, okay, and in order to solve these problems, we will actually start incorporating small amount of nonlinearity into the stream ciphers, but that actually makes it harder to analyze, okay, and therefore, it becomes not very popular. So, therefore, you have to make stream ciphers, I mean whatever ciphers you make, on one hand you have to make it secured, and on the same time you have to also make it amenable to analysis, because if it becomes harder to analyze, then you can neither say it is strong nor say it is weak, right. So, you have to show how you can actually analyze your cipher. Okay. So, we will take up this issue of this topic of linear feedback shift registers. So, I think broadly we can describe an LFSR of length L as an L stage. So, therefore, when I say delay elements in terms of hardware, I can just think in as a D flip flop. Okay. So, you can imagine that there are L D flip flops which are capable of storing 1 bit each, okay, and there is a clock which controls the movement of the data. Okay. So, you can understand that this is a shift register. So, what does it mean? That is, there is essentially a shifting in these arrays. Okay. Apart from that, there is a term which is called a feedback. Okay. So, there has to be some feedback at some place, right. So, therefore, you will see that and in case of an LFSR, you have this, like you have this structure, like you have got this array of, array of cells. Okay. So, you can, so there are L stages. So, which means that I can write like this is, say for example, S L minus 1, this is S L minus 2, and so on, this is say S 0. Okay. So, what happens is that if you, this is essentially also a shift register. So, therefore, there is a shifting among these flip flops, and there is also a feedback, right. So, this input is actually a feedback of the output of your previous flops. Okay. So, customarily what we do is that we can think in terms of AND gate here, and you can imagine that whether this connection exists or not, that is being denoted by some controlling values. Okay. So, for this, for example, we can say like C1, and we can continue like C1, C2, and so on till CL. Okay. And these outputs are essentially XORed here. Okay. Okay. So, this is an example of, so therefore, this is your feedback portion. So, this is your feedback, okay, and you can now understand, probably also say or appreciate why it is called linear feedback, because of these XORs. Okay. So, if I had replaced these XORs by say AND gates or some other gates, then this would not have been called a linear feedback shift register. Okay. And there are actually examples of something which is called a nonlinear feedback shift registers also. Okay. So, but we will essentially study with linear feedback shift registers, and this is how the diagram looks like. And this feedback is also sometimes it is called a connection. Okay. And this is sometimes denoted by something which is called a connection polynomial. Okay. So, I can represent or denote this feedback by a polynomial which is called a connection polynomial. Okay. And it is like this, it works like this, C 1 plus C 1 d plus so on till C L. Okay. So, I call it C L and d to the power of say L, okay, where L is your length. Okay. So, if I want an L, I mean if I want that the degree of this polynomial will be L, okay, then I have to ensure that the value of C L should be 1. So, therefore, that means that always this value of C L should be equal to 1. Okay. And what is that? I mean, and there are some merits why C L is kept equal to 1, okay, because we also want periodic sequences. Okay. So, this is how it looks like, and this is again a diagram, I mean a better diagram for the same thing. Okay. And this is denoted as L comma C D. Okay. So, therefore, L is the length and C D is your connection polynomial. Okay. And C D is as I told you is works out like this. And what is L? L is the length of the LFSR. Okay. And this tuple essentially defines a corresponding LFSR. Okay. So, we can consider a very simple example, like you can take a 4 stage LFSR for which the connection polynomial is 1 plus d power 4. So, the moment I say d, that means that this particular thing is connected, the rest of the things are not connected, right. So, you can take this polynomial and you can try to see how the sequences work. Okay. So, for example, you can just start giving some inputs like some arbitrary values like 0 1 1 0, okay, and you can start clocking the LFSR. Okay. So, you can observe that if you see the diagram, then this particular thing is a feedback, or rather is the feedback is an XOR of this output and this output, that is D3 and D0. The rest of the things are only shifts. Okay. So, you see that 0 gets shifted here, 1 gets shifted here, again 1 gets shifted here, and what about this value? It is a XOR of this value and this value, right. So, what about this value? It is a XOR of this value and this value. Okay. So on, you can work it out, right. And the rest of the things are only shifts, like 0 comes here, again comes here, again comes here, 1 comes here, comes shifts to here, right. So, what is the output of your LFSR? So, if you see the output of your LFSR, we have taken the output from D0. Okay. So, that means that last column D0 gives you the corresponding sequence, right. So, if you work out with this particular example, you will see that at 15th, so if I start with 0, at the 15th point you see that you again get back 0 1 1 0. So, 0 1 1 0 is the particular value with which you started with. So, which means that you have got a periodicity, but you have got a periodicity of 15, right. Why not 16? Because there is one missing state, and what is that? The all 0 values. Okay. So, in case of all 0 values, it will just get stuck up at its own point, right. So, therefore, it will not actually go to the next, go to another state. Okay. So, therefore, you see that you have got a periodicity, but your periodicity in this case is something which I called as a maximal. Okay. With 2 power of with 4 stage, with the 4 stage LFSR, there are totally 16 values, but out of them there are 15 non-zero values. Okay. So, you can, that is the maximum size of cycle that you can obtain. Okay. So, therefore, you see that these LFSR sequences are quite attractive because of this periodicity property. Okay. And that led to the lots and lots of study of its periodicity. Okay. And people try to figure out why it is periodic, or what are the properties that controls its periodicity. Okay. So, for example, like if you see that if your CD is a connection polynomial of degree L and is irreducible over Z2, then each of the 2 to the power of L minus 1 non-zero initial states of the LFSR produces an output sequence which is periodic. Okay. And what is the size of what is the periodicity? The periodicity will be the minimum value, okay, for which the connection polynomial, minimum integer value for which the connection polynomial divides 1 plus d power of n. Okay. So, therefore, that is the minimum such value for which it divides. Okay. So, this n will be actually a capital N. Okay. So, there is a mistake, this integer n and this is that integer n. Okay. So, in this case you will see that this, I mean, so therefore, if you take irreducible polynomials for your connection polynomial, okay, then you will find that it will be periodic, okay, and your periodicity will be actually the minimum value of n for which 1 plus d power of n will be divisible by C d, okay. That is that smallest value of n, and you will see that in all cases this value n will actually divide 2 power l minus 1, 2 power l minus 1. So, n will always divide 2 power l minus 1, okay. So, if I brief, what I am trying to say is this, that is C d is irreducible, okay. So, this implies that your periodicity or period will be equal to a value of n, or rather if I call it an n, and n will actually divide 2 power of l minus 1, okay. And in certain cases it will be actually equal to 2 power of l minus 1, okay. In those kinds of cases, in those cases when n is equal to 2 power of l minus 1, C d is actually called a primitive polynomial. Okay. So, what is a primitive polynomial? We can define it in this fashion. There are some other definitions of primitive polynomial also. So, you can immediately figure out that one definition of primitive polynomial would be like what I said you, that C d divides x to the power of n d to the power of n minus 1, right. So, therefore, in case of irreducible polynomial, so if you come to this particular thing, that is the minimum value of n for which 1 plus d power of n is divisible by C d, okay. And when this n is actually equal to 2 power of l minus 1, then that is called a primitive polynomial, okay. Another easy another definition, a basic definition of primitive polynomial is that you remember the finite fields, right. So, therefore, if you take for example the finite field z, okay, Zn star, okay, and you just start with any of the primitive elements, say you start with x, okay, and you keep on taking its power, like you take x, x square, x cube, x power 4 and so on, and whenever there is an overflow you do a modulo with the corresponding polynomial, and if you find that you are able to generate all distinct values in the field, then that particular polynomial, that particular reduction polynomial is also primitive, okay. So, do you understand what I am saying? So, what I am saying is that if you start with a polynomial, okay, and you take the primitive element, okay, and you take its power and you also take the modulo operation, using that if you are able to generate all the elements in your field, okay, when I am taking I am talking about the multiplicative part, okay, I am not talking about 0, okay. So, therefore, if you are able to generate all the elements, then that polynomial, then that particular reduction polynomial is also primitive at the same time, okay. So, in this case luckily 1 plus d power 1 plus d power of 4 was actually a primitive polynomial for finite field over 4. So, if you in terms of finite in terms of the Galois field notation, it is gf 2 power 4, okay. So, therefore, if 1 plus d power of 4 is actually a primitive polynomial of gf 2 power of 4, and therefore, actually the periodicity of the corresponding LFSR was equal to 15, which was equal to 2 power 4 minus 1, okay. So, the next question that we will take up, and is actually quite a non-trivial question, that is, can I reconstruct the LFSR, that is, given a sequence, can I actually reconstruct back the LFSR. So, therefore, if I give you a sequence and the question is, can we reconstruct the LFSR with generates a sequence. Do you understand the problem? Okay. So, now the problem that I am talking about is that if I give you the corresponding output sequence and I want back the LFSR. So, there are two things that is important. One is the length of the LFSR, and the second thing is that the feedback of the LFSR. Okay. So, I need to compute both the things. Okay. So, there is a term which is called linear complexity, and this problem is essentially something defined by something which is called a linear complexity. Okay. So, therefore, an LFSR is said to generate a sequence S if there is some initial state for which the output sequence of an LFSR is S. So, this is a quite simple definition. So, this is just to define what you mean by generating the sequence, and if the sequence has got a finite length n, then we will use Sn to denote that. Okay. So, what is a linear complexity? So, linear complexity of an infinite binary sequence S is denoted as follows. If S is a 0 sequence, so 0 sequence means all zeros, then I define Ls to be equal to 0. If no LFSR can generate S, then Ls is actually equal to infinity. Okay, that means it's Ls is equal to infinity. I mean, all these things will make sense with this third point. Okay, it says that otherwise Ls is the length of the shortest LFSR that generates S. Okay, so this L is something which is called the linear complexity. Okay, so what I am interested is in finding out the smallest LFSR which will generate a given sequence. Okay, so therefore there are two things that I am interested in, if you understand. One is the length of the LFSR, what is the smallest length which generates it, and the other thing is that what is the corresponding connection polynomial, right. So, how do I understand that? Okay, so let us start with a simple example. Okay, and there is I mean, it is better to start with the example, because there is a quite involved algorithm in, I mean we will just decide whether we will go into in depth or not, but at least we will try to appreciate what is meant by a linear complexity. Okay, so therefore let us try with this simple example. So, let us try to reconstruct an LFSR whose sequence is say 0 0 1 1 1 0 1 1. Okay. So let us start with only these two 0 0. So, immediately you can understand that if you have got two corresponding next to next zeros, subsequent zeros, then your LFSR length cannot be 2, right, because if your LFSR length is 2, then you are getting stuck up at that point, right. So, it has to be more than 2, right. So, therefore, what is the size that you can start with next? It is 3, right. So, let us take 3 such D flip flops, okay, and try to work out. Okay, so, we take like S, so I call that say S2, S1 and S0, okay, and let us try to generate 0 0 1. So, you can see that if it is 0 0 1, then the first thing comes out is 0, then you again 0, and then you have got 1 here. Okay, and what you need to figure out is whether this particular thing is connected or not, right. So, therefore, what is the corresponding value of C1, what is the corresponding value, this is an AND gate. Okay, so, therefore, this is a, there is an XOR here, there is an XOR here, there is an AND here. So, you have a C2 here, and I am connecting this value because I am taking this to be 1. Okay. So, right. So, this is how your diagram looks like, right. So, what I am interested in is in finding out what is the value of C1 and C2, right. So, you see that if I take this 1 0 0, then what is the corresponding next sequence? It is 1 comes here, 0 comes here, okay. Then again this 1 comes here, and this is my, and this is the output which is being generated, right. So, therefore, you have got 0 0 1 and so on. So, what is the next sequence? It is 1 here. So, you can take this one and put it here, and this one will come here. So, therefore, I can write some equations like I know that the next thing which is to be fed back is 1, right. So, immediately I know that 1 is equal to C1. So, what is the corresponding value here? Yes, this is 1 here, C1 XORed with 0, and this is 0. So, this is 0, right. So, that means C1 is equal to 1. What about the next thing? The next thing in the sequence is also 1. So, that means this is a 1 which is again to be fed back. So, you know that 1 is equal to, so you know that 1 is to be fed back, yeah. Yeah, so if it's 1s or C1, no, C2, right? Yeah. Any other thing? That's fine. So, that means what is the value of C2? It is 0. Okay. What about the next sequence? It is 0. So, you should get back here 0. Are you able to get back 0? So, you see that the next thing that you get back here 0 is suppose this is 1 and this is 0, okay, then you are actually getting back 0, right. So, therefore, you see that you are getting back, you are getting 0 0 1 1 1 and 0, okay. But what about the next thing that you will get? You will actually not get up, you will get 1. Will you get 1 next? You are getting back 1 also. You see that? But there will be a problem with this one. So, here instead of 1 you will have 0. So, that means that this particular LFSR configuration cannot generate beyond this, right. So, you see that is, so you start to understand that there is something which is called the smallest possible length, okay, and therefore, you need a bigger LFSR to do the thing, okay. And you can actually work out this example with a 4 stage LFSR, and you will find out that there will be some inconsistencies in the equations, for which you can understand that a 4 stage LFSR will actually not give you this sequence also, okay. So, actually it will be a 5 stage LFSR which will give you this output, okay, and the equations will become only a little bit more complex, okay. So, what do you understand that if you write in such kind of, in such a fashion, and you obtain a linear system of equations, then you can actually solve them, right. You actually require 2n number of bits to solve these equations, okay. But the thing is that the solving becomes easier by a certain approach, okay, and that approach is known as the Burle-Massey algorithm, okay. But this essentially gives you an idea. So, what we today discussed is about a basic idea that there is something which is called the smallest possible length of an LFSR which generates a given sequence, okay. So, that means that you start to understand that you need a bigger LFSR to generate the corresponding subsequences, I mean the subsequent sequences, okay. So, you can ponder about this particular point, and you can just think of this point, that what we have discussed is about an LFSR which has got no all 0 values, that can you modify the LFSR with connection polynomial primitive to include the all 0 state, okay. So, some of the references, you know, that I followed a little bit of Stinson's book, but mainly I have followed Menez's handbook of applied cryptography. This book is actually available online, okay. So, you can actually download this chapter, it is chapter 6 of this book, and you can study this chapter also, okay. So, we will continue with stream ciphers.